Hi, everyone. Welcome to the talk on concurrency analysis platform and tools for finding concurrency bugs. I'm Madan Musuwati. I'm from Microsoft Research. This is joint work with Tom Ball, Tom Ball's right here, Sebastian Burkhardt, myself, and Shaz Kadir. Shaz, are you around here? Maybe he'll come in. Just to give you a background, we work a lot on building analysis tools to improve both developer and tester productivity. And you're going to see this tool. Today we're going to be focusing on concurrent programs. There we go. So I know many of you here would have had experience developing concurrent programs, if not developing, testing, or even horror stories about how difficult concurrent programming is. Okay, so the main problem is that the program execution is so non-deterministic. You run it once, the threads interleave in one way, you get one behavior. You run it again, you get a totally different behavior. So what this means is that there are some bugs hidden in your program that show up very rarely. You have your program that's running perfectly fine for a couple of months, and suddenly it crashes. Now you want to debug it. How will you debug it? I mean, you want to make it crash in a debugging scenario. And what is worse is that slight changes to your program can completely change the set of interleavings that you explore. Right? You have your release version, which is crashing once every 1,000 times it runs. You run in a debugger, your debug version never crashes. So let's say you want to do some printf debugging. So you add a printf statement in your program. Again, like in your program, does not crash at all. Right? Now this is why it's called a Heisenberg bug, because just observing the bug can fix your bug. Right? And so it's a huge productivity problem, believe me. Like, people can spend days, weeks, and even months trying to just reproduce a bug, leave alone just debug the bug. Right. So we are going to give you a tool that will solve this scenario. So what are you going to see in this talk? First of all, we'll present a tool called Chess that will help you find and reproduce deterministically your concurrency bugs. We have this tool working both for native as well as managed programs. We'll be demonstrating both. And this is Chess is far from being a research tool. We have worked on Chess for almost 2 years now. We have a lot of product adoption inside Microsoft. You'd have heard some of these products already. You've heard from the parallel computing platform PCP that produces things like P-Link, TPL. They are customers of Chess. You heard of Singularity Operating System, which is a research operating system from Microsoft Research. They have been using Chess, and also to products like Dryad and Cosmos. And so just to give you an idea about the maturity of the tool, we have several product teams using Chess, and this is the first time we'll be announcing Chess to our external customers. So you'll get more information about this in this talk. So first of all, I want to dive into a demo just to give you guys, how difficult concurrency really is. You guys don't really need the demo here, but sometimes it's much better if you really see your own pain. Okay. So what I'm going to do is I'm going to start very small, an academic example. This is sort of the example that a program that first-year undergraduate student would write when he's first introduced to concurrency. Nowadays, people start programming at 13. So, okay. So at 7. Okay. So what I wrote was a concurrent class called a bank account. And you see here is a variable that represents how much money you have. And then there are 3 functions. A read method that will read the current balance. So just since it can be called by multiple threads at the same time, you make sure you enter a lock, you enter the critical section, and now read the balance, and then you leave it. So this is sort of well-synchronized method. And then you go to the deposit. You want to deposit some money. You again acquire the lock, update the balance, and you release the lock. Okay? But if you look at the withdraw method, it has a concurrency bug. So it's calling the read method to read the current balance into this temporary variable R, and then updates the balance after acquiring the lock. And so if you look at read is actually releasing the lock here, and you're reacquiring here. So between the read, after the read, and acquiring the lock, okay, there's a small window of opportunity where somebody else can come and update the balance. And if that happened, the balance you have in this variable R is stale, right? And this is called an atomicity violation because you wanted the withdrawal method to update the balance atomically, and because of the way you've done the locking, you've screwed up. Okay? And this is a very simple bug, a simple program with a simple bug. Let's try to find it. Okay? So I wrote a test case here called run test. So what it does is creates a bank account, initializes with $10, and then it creates a thread called the withdraw thread. Let me move this a little bit here so they can see that. It's called the withdraw thread. And while the withdraw thread is running, it's going to call deposit, and it's going to deposit $1 to the account. And the withdraw thread is going to, withdraw $2. So what you have in this test is deposit and withdraw happening concurrently, and because of the bug, they can mess each other up. So I have a bank account which is $10. I'm depositing $1. I'm withdrawing $2. So I want the final balance to be 9. And if the final balance is not 9, I'm going to say my test failed. I'm going to print false. Otherwise, I'm going to say print true, saying that the test succeeded. So let me build this program. Okay, just to show it's real. Okay, and now I've written a program called run DLL, and what it's going to do is that it's going to run the test 100 times. Okay, and you can see it ran 100 times, and it did not find the bug. If it had found the bug, you would have printed false instead of true. Okay, just to show you what exactly happened. This, by the way, is a dual core machine. It's a laptop right here. And so you have withdraw and deposit running concurrently. So the bug is theoretically possible to, it's theoretically possible that you'll see the bug when you run it. But this window here shows the interleavings that the program explored. Okay, let me explain this GUI. It has multiple columns. Each column represents one run of the test case. So if you look at this one here, the purple thread ran for 4 steps, which corresponds to 4 synchronization events. And then we switched over to the green thread. This was the withdraw thread. It did some 5 steps, 5 synchronizations. And then we switched back to the purple thread. The important thing here is that I ran it 100 times, and I explored the same interleaving, right? And no wonder you did not find the bug. Okay? So what people do here is like, hey, let's stress the program. If I run it just like this, I'm not going to get any interleaving variety. So I'm going to run some stress. So what I did was that I have a stress option. And what this is going to do is going to run the program while creating a lot of background threads. These background threads are, creating other threads, allocating memory, doing lots of computation, doing random sleeps. What else? Yeah, and actually blocking, and all these things just to simulate how the program would have run in a typical stress scenario. You can imagine there are around 1,000 threads when this program is running, along with the 2 threads that is doing the balance and so that is the withdraw and the deposit. You can see that I'm just bringing this laptop to its knees right now. It's like CPU usage is 100%. I'm doing a lot of work. There's so much of non-determinism in the system, and I'm feeling so good about myself because I wrote this program. I stressed it so much. It didn't crash. It didn't find the bug, and so my program is right. Right? Let's ship it. Cool. And just to give you some window as to what exactly happened. Let's see what happened. Oh, okay. So we did so much of work. We did get some interleaving variety, right? You see that the fourth execution right here is actually we took a different interleaving, but the remaining, we were not that lucky. Sometimes when I give the demo, I see a little bit more variety. It depends on the temperature of the room, whether the lights are on or off. Like, a lot of non-determinism out there, folks. But again, the thing is that we did not find the bug. And it was a simple program. It's the simplest concurrency mistake anybody can make, and stress is not able to find it. I can run the program again, but you're going to see similar behavior. So let me go back to my talk. So the fundamental problem is we have no control over how the threads interleave. And it's very clear that the program behavior depends on the interleaving. For the bug to show up, you have to, the deposit thread has to interfere with the withdraw thread in a particular way, right? Now, okay, so sorry, we have some problems with the slides. But anyway, so if the interleavings are so important, why can't we give the control to the user? And that's what we are going to do. So we have built a platform called the Concurrency Analysis Platform, CAP for short. And the basic primitive is that you decide what the interleaving is. You say, okay, here's my program. Here's an interleaving. Please run this program on this interleaving, right? It's a very simple primitive, but if you think about it, doing this using traditional methods is very hard. Imagine if you have to go into your debugger, set breakpoints, freeze threads, unfreeze threads. You have to do a lot of jugglery just to drive the program along one interleaving. So what CAP gives you the ability is to just say, okay, here's a program, here's an interleaving, run it. And not only that, we actually have a programmatic API. And so what this means is that we can have analysis tools that tell which interleaving is more interesting. And that's what gives us a lot of power. So you can say, here's a program, here's a set of interleavings, run this program on this set of interleavings, right? Or if you're a tester and if you just found an interleaving that produces a bug, you can tell the developer, hey, developer, here's a program, here's an interleaving that produces a bug. That's your repro case, right? And in fact, the first two bullets comprise what we call the tool chess that you will see for the rest of the talk. Chess is built on top, is one of the tools that is built on top of the CAP platform. And at the end of the talk, I'll give you some some other tools that we are actually building on top of this platform. Okay. So now let's see the CAP and chess working on this demo. So believe me, now we'll find the bug. So remember that previously I was running stress on this balance.dll, didn't find the bug. Now I'm going to run chess, and there we go. So what happened here? It happened very fast. Okay, so thank you. Let me do it again. Feels so good, right? So what happened? Thank you. So what happened was that chess used the CAP platform to say, okay, run the balance.dll on this interleaving. So and then tried a different interleaving. So systematically try different interleavings, and the fourth attempt it actually found a bug, right? And this has become more clear if I start our GUI. You can see, right? These are the four interleavings that we explored. The same picture, every column represents a run of the program, and the purple thread and the green thread are the two threads. You can see that we tried different interleavings. And for the simple program, we found the bug very, very easily. And that's how life should be, right? And you can actually, so what I demonstrated right now was actually a command line tool for the native version of chess. And in the rest of the talk, you'll actually see how we have integrated chess with Visual Studio and how we can make it much easier to use. But just to go under the wrap for you guys. Okay. Yeah, this thing is not. Okay, so now let me go and explain a little bit about how CAP works. So you have both unmanaged or a managed program. It's using the underlying operating system or the CLR for its concurrency, right? It's making API calls to create threads to do synchronization. And what CAP does is that provides hooks, like a thin sliver of code between the program and the underlying operating system, so that it gets control whenever the program makes a synchronization operation or a threading operation. And so this allows two important things from CAP. Is that first of all, when the program is running, we can record what the interleaving the program is executing. And more importantly, CAP can direct the program along an interleaving of its choice. It can say, OK, this thread is trying to acquire this lock. Maybe I'm not going to allow this thread to acquire the lock right now. I'm going to insert a delay and switch to another thread. So CAP controls the scheduling of the thread. And the operating system no longer has any non-deterministic control. Like CAP takes complete control over all the non-determinism in your program. And it exposes this API to build lots of tools, that we are actually exploring that we can do on top of CAP. So you're going to see some chess today and some of the other tools that we have built on top of CAP. You can have like data race detection tools, testing tools, coverage tools, and visualization tools too. So a high-level message of this slide is that today you're just going to be seeing the tip of the iceberg from what we are able to do. So just look to us for more tools in the future. So just to go into the details, I know that you guys really want to know how this works. There are actually two very important challenges in building a tool like CAP. First of all, we have to understand all the synchronization primitives, because what we want to do is we want to be complete. If a bug shows up in the wild, we want to be able to reproduce it when CAP is under control. So what this means is that we need to understand what locks are, semaphores are, what APCs are, when timers can fire, because we need to understand the semantics of all these complex APIs and explore the non-determinism involved in these APIs. The good news is that we already do that for you. If you're using the Win32 threading API or the system.threading in the managed case, we already support those APIs. But we could support any other concurrency APIs that you're going to be using in the future. You would have heard that Microsoft has this new set of APIs like P-Link and TPL that allows you to write concurrent programs much easier. So in the future, you can envision a tool like Chess that supports those APIs as well. And another important thing is that you don't want to introduce false behavior. So essentially, we take a program which is running under the operating system scheduler, and we're replacing the scheduler with our own scheduler, right? It'll be very frustrating in this process if we introduce new interleavings that are not possible in the reality. Then we'll be finding bugs that are not real bugs. That is a very frustrating process. So not only do we have to be complete, we also have to be precise. Now, doing this both together is a very hard problem. And I can go over the details more if you visit us in the booth. Pardon? Yes. So so we also have these experts at lounge at 6 o'clock. So please show up there. We can tell you more. We can drive into the details of all this. So at this point, I'm going to ask Tom to come over, and he'll explain, demonstrate chess. Thank you.
Great. OK, thanks very much, Madan. Hi, I'm Tom Ball. And in the rest of the talk, what we'll do is do a deeper dive into chess, which is this testing, systematic testing, and repro for Heisenbugs, and show you how we've recently integrated that with Visual Studio. We'll first start with the simple example in Manage Code, the bank account, But then we'll go on and show you a demo where we worked with George Chrysanthopoulos, who's the author of the Concurrency and Coordination runtime that we just announced the availability of today. And we'll show you how we found a Heisenberg bug that he had reported to us. Then Madan will come back on stage and talk about the future plans, future tools that we have in the pipeline. And please, as we're going along, if there's anything confusing or you have any questions, just raise your hand and let us know, because we have plenty of time. Yes.
So if CAP can sort of inject into the runtime and take control of the timing and sort of run everything without the non-determinism, why don't we just ship everything on CAP and run it like that?
So there is a notion. There is a notion of. Sorry. Repeat the question. Why don't we put this just into our scheduler? Why don't we have this ability to observe and control the non-determinism just built in to the fundamentals of the scheduler? I think that's a very good question. I think that there are, as Madan said, difficulties in sort of the layer of abstraction we have. We've thought about it, like if you were to put this into the kernel scheduler, wouldn't that be a great idea? Well, maybe, but that's pretty low level of abstraction. You'd start to see sort of behavior from a lot of different places. So the level at which you put these wrappers or this technology, we're not exactly, there's different trade-offs, first of all. But I think it's a very good point. I mean, we want our systems to be reliable. In order for them to be reliable, they have to be observable and controllable, which really means testable. And so, I think fundamentally we would like to see this sort of capability built in. It would simplify our lives in terms of writing CAP, because as you said, it would sort of be there. So I think it's an interesting thing for the future. Yeah. Okay, so we're going to go out of C++ right now, and we're going to look at a C# project in Visual Studio. And here I have a piece of code that implements a bank account. Maybe it has a bug, maybe it doesn't. You can guess what the bug might be. But what I've done here is I've made use of team tests to create a unit test. So here I have a test method, and what I'm doing is very similar to what you saw in the code that Madan showed you. So we're going to create an account with 10 ints. We're going to create a child thread that's going to withdraw 2 ints. And we're going to start up that child on the account. And then in parallel with that, we're going to deposit $1 in, wait for the child, and then we're going to use the assert functionality in the unit test framework to assert that at the end we expect that the account should be $9, so 10 minus 2 plus 1. Okay, and you see the failure here. That was from a previous run. Let's get rid of that. Let's just run this using the unit test framework. So we run this in the current context. And what it's basically doing is it's running it just on .NET, right, without chess. Okay, and so this is essentially the same behavior you saw with Madan at the command line. And if I widen this window a little bit, I can get a run button, and I can click on this. And I click, and I'm getting this happy, warm feeling that things are all right. I can put this in a loop. As you saw, I can make it go 100 times, 1,000,000 times. I can introduce stress. But still, I may not find the bug, if there is one. Okay, so the way we've integrated chess with Visual Studio is very simple. We essentially define a new host type. That is a new way of running tests. And so all that I need to do to run chess here is to say, I've got a new host type. And guess what? It's called chess. Okay? And now let's go back and run my test. Okay, now you'll see a window pop up. That's just to show you that chess is running there. We don't have to show it. But you see 1, 2, 3 schedules, and lo and behold, there's a different result. There's the failure. So that's essentially what you saw on the command line now integrated with Visual Studio. And remember that order in which the schedules are being visited is deterministic. So if I didn't find that by chance, and as Madan showed you repeatedly running the test under chess, if I run it again, I'm going to get exactly the same behavior, okay? There's no random numbers being generated, no random sleeps. It's going to fail deterministically on the third schedule there. Okay, so now how do we do our debugging? So Madan showed you the bug, but suppose I didn't know about this account class, and I now know there's a bug. How do I find it? Okay, so in this case, let's click in. And what we see here, and pardon me, the font, I could never make it large. We see here that the assertion failed, as we expected 9, and the actual value was 8. Okay, so that was the test failure. And below this, we see that chess gives us some information. 4 schedules explored. It was actually the 4th one that caused, I think, the error. 2 preemptions per schedule. I'll explain that in a little bit. And then it told about the it tells you about how to do the repro. Okay, and so here is our lightweight integration of chess into Visual Studio. We copy this little piece of code, and we plug it in here at the beginning of the test method. And you see 2 things here. One is a string that is totally incomprehensible to humans. Okay? And you can see here I have a little region around it, and that's for a good purpose. Get rid of it. What that is that's the chess schedule. Okay? And that was generated by chess. It represents the interleaving of thread events that led to the bug. Okay. So now I also have 2 other properties. I have a test property that says, now when you run chess, please run it in repro mode. So we have 2 modes in chess. We have what's called explore mode, where we're trying different schedules, and then we have the repro mode, where we're using a schedule that's stored somewhere here in the code, in this case, but maybe in a database or such. And then we have also a debugger command. So chess has this notion of preemptions, and what is a preemption? It's just an interruption. It's when chess or a scheduler decides that one thread should just stop executing, and it gets interrupted and runs another thread. Okay, so we can run this test in 2 modes. We can just say, please, just please rerun the test for me. So run the test. Now you won't see the window pop up, but in the background, chess is running, and it says failed. So that's just a deterministic repro where chess is using the schedule string. But what's more interesting is that we can run this now under the debugger, and now chess will break at each point in the schedule. At each point in the schedule that it switched from one thread to another, more precisely when it interrupted the thread. And we'll see that now. Okay. So let me just make the window a little different. Okay, so what I've got here is I've got the threads in my program at the top, and I've got the call stack on the right, and here we are at our first preemption. So what's happened in this schedule, in this buggy schedule, is we've run the main thread to just the point before it acquires the lock. Okay, and if we hover over balance, we see that balance is $10. Okay, now if I hit F10, in a normal debugging situation, whatever threads are enabled will just run. But now, under the control of chess, I go to the client, or to the child thread, and I read the value of balance into temp. So temp is now 10. And you see the buggy code again. And now what you see is the second preemption point. So chess is instructed the debugger to break just before acquiring the lock. And that's just the point we need to preempt at to find the bug. Okay? So now what's happening? Well, we have to switch to another thread, and chess will tell us which one that is. And that's the main thread. So now we go in and update balance. So now balance is 11. Okay? We come out of that. We join up with the child. But the child has a little bit more work to do, but now we're in big trouble, right? Temp is 10. Temp is the old value. It's a stale value. Balance is currently 11. We're going to do 10 minus 2 equals 8. Overwrite balance. And now the assertion will fail. Okay? Okay, so that was to show you sort of more completely what's going on with chess. So systematic exploration of schedules Okay? Once you find the schedule, we have it. We have a string. We can store it in a database, and then we can run your program over and over again. And it's totally deterministic. Now it's like running a sequential program. It's a sequential debugging experience. Okay?
Does that always go? I mean, if you have other threads running that are dependent on IO
yes,
taking
yes.
longer time and your delays.
Okay, so the question is, what if I have other threads in my system? It can be okay as long as you're isolated from those, right? Now, say that you created your test case with these 3 threads, but unbeknownst to you, you called into some library that did some COM or some messaging with another component in Windows. There's non-determinism there. Like, when do I get the message back? And if we didn't wrap that and control it, exactly. So you need to think when you're testing your system about carving out a space, that you're testing, and you need to think hard about, what are the possibilities for interference. If chess covers those possibilities, you're good to go. But if there are other things, other APIs you're using that chess doesn't know about, then you may not have full deterministic repro.
Question.
Yeah, I'm sorry. Go ahead.
So the demo that you just ran, it represents a case in which you've already identified a potential threading bug, right? And you've remembered to assert for it. So you already know what potentially could go wrong with your code. But does it help you in any way to sort of identify those cases that could potentially be affected by the interleaving?
That's very good. So we'll actually get to that when we look at CCR. There's a whole class of concurrency bugs. So what I showed you here was finding an assertion violation, which was just in the code. Now, that assertion was actually not really necessarily about concurrency. It's just my expected behavior of the code, whether it executes sequentially or concurrently. So that test was not really, the assertion wasn't designed explicitly with concurrency in mind. Of course, the test case made things concurrent. But even if it was sequential, I would still expect that. But there are a class of errors that are specific to concurrency. Data races, which may or may not lead to errors, deadlocks, and live locks, and we'll get to that. In fact, I was supposed to show you this slide before I showed you the demo of chess, but I got so excited I wanted to show you the demo. So what did I just show you? I just showed you the following. So I showed you chess, and essentially what was chess doing? It was running a test scenario in a loop, and the guarantees are 2. 1, that every run takes a different interleaving, so you're getting more coverage than you would with stress. And 2, since chess is storing as it processes the schedule and determines which schedule, it stores it away. If you have a violation, assertion violation, then chess will give you a repro case. Okay, so it uses the CAP scheduler underneath to essentially do the API wrapping and get access to all the events that matter. Okay? And now what can chess discover? Well, chess can discover any assertion violation. So of course, in good programming practice, we're all putting assertions in our code. Right? We're looking out for the border cases. We have all sorts of stuff in our code, and we can just leverage that. So as we're running your code, we run your asserts. You should run chess, under your debug build. But chess, because it knows about concurrency, it knows about the synchronization, the locks, it can detect deadlocks where nobody's making progress. It can detect data races. We don't have that demo here today, but we're building that in. So it can say, look, I've got a read in one thread and a write in the other, and they're unordered. That is, there's no synchronization that guarantees me that the read always comes before the write. So there might be another order where the write comes before the read, and you might get different results. And then also, chess has the ability to find live lock. So this is sort of lack of progress. So all the threads are doing things, but nothing's happening in your system. And we've sort of seen that a number of times in various programs we use where you're waiting on a program and it seems to be spinning but not doing much. Yeah. Very good. Yes, we will get to that. So the gentleman is saying if you have a program with loops and it's very large, and even if you have, then you have an enormous state space, right? Right, yeah, we will just hold that thought. We will get to that question. Yes?
Could just be combined with other tools like PHP for application verifiers?
Yes, actually, we can run any sort of monitoring framework. Chess is running your program. It's really running your program under a test. So any runtime technique that can attach to your process, like app verifier, yeah. In fact, we use chess in that mode internally. Good question here.
Can control several processes at the same time?
Okay. No. Can chess control several processes? In theory, yes. Currently, what we've implemented is controlling the threads within a single process. But that has been a request that we've had from quite a few people, and that's quite possible. Yes? Do we have Visual Studio integration for unmanaged code? We have a plan that but we don't. So the answer is no. But in that unit test framework you saw, it should be possible to just have a managed wrapper calling your unmanaged code. But we also have the command line tools. So that's under discussion how to do that. Yes.
The Visual Studio unit test stuff. If you make a change to resolve the bug and you leave all that debugging.
That's another great question. So what if I change my code and you leave all that stuff in there? Hold that thought. We'll go back to the demo and look at that scenario. We do want to fix bugs, and I didn't show you that. Okay, yes. One more, and then I think we should progress. We'll take some more questions later. Yeah. Code that runs in services. So right now, chess is in a single process. It's just dealing with multi-threading. So if you got a service with message passing, no. But that's a scenario we love to try to go at. But we don't have any experience with that yet. Okay, let's just move on a little bit. I want to tell you about this gentleman's question, which was about, can you make this stuff really work? You showed it to me on this balance example, this tiny little program. How can it possibly work in practice? And to sort of give you the research mathematician viewpoint just a little bit, because we're researchers, let's look at how big the problem is. So suppose you have n threads. So here in the picture you have these n threads going across n columns. And each of them has k steps. These are just execution steps. Let's assume they're atomic. So each assignment there. But think of k as the length of your execution. Okay? Then how many different interleavings do you have? Well, if you do your big O analysis, the number is really big. It's order n, the number of threads, raised to n times k. So it's exponential, both in the number of threads and k. So choose n, your number of threads, to 2, and k equal to 100, and that number is now greater than the number of atoms in the known universe. Okay? This is what people call the state space explosion. And if you saw the Turing Award winner for this year, it was 3 people who worked on this idea of model checking. And the key problem in model checking is when you take n concurrent processes or threads and combine them, you get a lot of states. So this limits the scalability to large programs. In particular, even if we shrink n to be very small, you see that for even moderately small or large k, depending on your notion of small or large, 100, you have a very big state space. So how are we going to scale chess to large programs that we might be able to control the number of threads, but how can you control how long your program executes for? That's sort of tough. So we're concerned about both n and k, but in particular k. So here's the basic idea. We want to focus on the schedules first that are going to find us the bugs. And we believe that by focusing on executions with smaller numbers of preemptions, we'll find a lot of bugs, and we can explore those schedules very quickly, or at least within a day or so. So what's a preemption? Okay, a preemption, as I said before, is just an interruption. Okay, so we think of code that's running. And here's a classic example. I don't have any locks. And thread 1 is doing a check of a pointer p against null. And the other thread is setting p to null. And if there's a preemption, an interruption of thread 1 after it's determined that p is not null, and then thread 2 comes along and sets p to null, you've got a problem when you dereference p. So this is a classic idea of really an atomicity violation, that you really, for most atomicity problems, you really only need one preemption, but you just have to find just the wrong place for that preemption to occur. So you don't need hundreds of preemptions to find bugs. You need very few. Okay, and we're just in chess, we distinguish between the preemption, that is the unexpected interruption, from the non-preemptive event. That's a context switch that you have to take because, say, you tried to acquire a lock and you were blocked, or your thread ended and you had to switch to another thread. Okay? So this is the key idea of chess. Let's enumerate the schedules using a bound on the preemptions. Okay, so let's introduce, as we usually do when we're confronted with these large numbers, n to the nk, let's introduce a new variable, c, a new parameter, which is a budget. It's the number of preemptions chess gets to use for each test run. And c is going to be small. So let's go back to that example where we had 2 threads and 100 steps. If we limit ourselves to 2 preemptions, c equals 2 per schedule, then we only have less than 1 million interleavings. Now remember, without that c equal 2, and n to the k was greater than the number of atoms in the known universe. So by introducing this notion, this useful notion of preemptions, and by exploring first schedules with fewer preemptions and then growing to larger numbers, we can actually make chess scale. And we have a lot of other analysis techniques we can't talk about today to reduce this state space further. Sometimes 2 different interleavings yield the same state. And you can do things to identify that. You can get rid of even more. Okay, so now we're going to go back to our demo and just finish it off. So we had a gentleman who asked, well, what if I change my code? Let's go in and fix the code and take that read and put it inside. Well, as soon as you change the code, the repro string that we have is out of date. So I could run this, but it's going to say test inconclusive. And the reason it would do it is chess would say, I'm getting an event in the program that the trace says shouldn't occur. Okay. So generally, when I want to when I change the code, I should always sort of eliminate my old repro. So let's run again this program under chess. Okay. So now it's going to come up, and we're going to get a lot more interleavings, right? Let's watch. Woohoo! 5. Wow, that was great, and we got a green. Now you're all thinking, are we done? Right? Are we done with testing? Now this is a very small program, and I think for this program the answer is yes. But you might also be wondering how many preemptions did I use? And by default we use 2. So let's do something. We have another property. We have chess bound, which is the number of preemptions, and we can bump it up to 3 and see what happens. Whoa! I don't know what I hit there. Excuse me. Okay, let's run that again. And now it's running with 3 preemptions, and same 5 schedules. So we could pump it up to 10 too. I don't know, 100. But there's no guarantee that if you get the same number that you've converged. But for this small example, it's a pretty good bet. Let's do it at 100. See if we get any more. No, there just aren't any more. Okay, so chess has this enumerative philosophy, and we guarantee that within that bound, if we terminate, we've covered all. Now, does it mean the program's correct? Well, in this case, it's so small by observation we can say. No, I mean, generally you have a test case. We're doing the interleavings with respect to a specific test case. Maybe there's another test that would cause this program to go wrong. Okay, so now we've showed you the basic idea of chess. I want to now talk about some real code. Okay, and we've been working with George Chrysanthopoulos who's the creator of the Concurrency and Coordination Runtime. It's used inside Microsoft. It ships with the Robotics Studio. It's used by some partners now, and it's available. And essentially, we had told George about chess and made him aware of it, and he sent me an email. And this is a great email because it really demonstrates the issues we have in concurrent systems. So they have a BVT, a Bill Verification Test Pass. They run it nightly. And he said, hi, Tom. Today one of our BVTs failed, and they haven't failed in a long time, which means there's some very rare race in either the multiple item receive primitive or something more fundamental. And fortunately for us, he has a test framework that's pretty big. He pointed to the unit test, and he said, this unit test, iterator with multiple item receive many ports, this is the one that didn't terminate. is this something you can throw chess at to see if it catches anything? So this was great. This was back in January, February, March, April. And so I want to show you what we did with chess. Whoops. And we can just keep that up there because we're going to switch back to this machine. OK. So let's switch to CCR, make sure we have the version that has the bug. OK. So CCR has a couple projects. The core, which contains all the CCR primitives, some adapters. He has a unit test project. And what I did was I just created a new project that just calls that function. Now, if you go to his code, he does the standard thing of repeating the test many times. I think the number he gave instead of 1 was 100,000. He said, repeat this test. So this test has a subtest in it, and he would repeat it like 100,000 times. But with chess, we don't need to do that because we're being very systematic about interleaving. We don't need stress. So we actually gave it a value of 1. And that's good because there are less synchronization operations. K is smaller. The number of steps is smaller. So whatever we can do to make chess's life easier is great. Again, if we run this without chess, there's not going to be any surprises. We're going to get green. But really what's nice here is to show you chess in action. So here, we're going to see a couple of things. One is there's a lot more interleavings than we saw before. So now we're getting into the hundreds. And in about 4 seconds, we've explored 1,000 different interleavings or schedules. 2,000, 3,000, 4,000. Whoa! Deadlock. Oh, what was that? So this was my experience. Once he told me I had a Heisenberg, it was in this test. In under a minute, chess found it. Okay. So we were like, hey, that's wild. I mean, we were like jumping up and down. It was like, woohoo! It was great. Okay. So now you know the story from here, but the story is a great one because now, I mean, I could have given this repro to George if we had the Visual Studio integration at this time, and it could have been his job to go and do this little task I'm going to show you now. But it's so easy now. So now, again, I have that big string. I have lots of different ways of talking about concurrency. So I can tell chess, please take me to the deadlock state. Okay? So it's basically going to take me there. And when chess finds the deadlock, it's going to break. Okay? And remember, it's going to happen really quickly, because that's just one schedule out of the 4,000. So I don't have to wait half a minute. I just wait until I get that. So now what do we have? We have the call stack. So let's see. We have 3 threads. We have the base thread. What is the base thread doing? The base thread is waiting. Actually, do I have the right one? Let me make sure. No, I didn't select it. I want to select the main thread. Okay, what is the main thread doing? The main thread is running the test. Okay, here's the test, which is posting something. And then the test is waiting for the children to finish up. The children are these things called task execution workers. What are they doing? That one's waiting. What's it waiting for? It's waiting for work from the main thread. What's this guy doing? Oh, it's waiting for work from the main thread. Okay, so that's the deadlock. Now, how do we get into that deadlock? That's more interesting. So now I can stop my debugging. So now I know sort of why I know that I'm in a deadlock. How did I get there? Well, remember, chess is very valuable. Here I'm running with 2 preemptions. And in fact, this bug requires 2 preemptions to find. If you run it with only 1 preemption, you don't find the bug. So you need 2 preemptions. And now I just tell chess, break before those preemptions. And this is really what led me to the scenario that I communicated to George. And he said, oh, I know what the problem is. So basically, what I see is the first preemption is happening. And what is this code doing? It's registering to receive some work. Okay, great. Let's hit F5 and go to the next preemption. Now that's this guy right here. It's still registering to receive work. What's this other thread doing? It's cleaning up. One is registering to receive work, and the other is tearing it down. So that was sort of an indication that there was a race, that these 2 things were going at the same work. And in fact, that's what essentially was the hint, the clue that led us to the bug that George has fixed and is no longer in the no longer in the product. To show you that, let's go to the code with the bug fix, and let's start that up and running under chess. Okay. So here, again, just to show you the power, how long is this going to take? Don't really know. So we have n to the nk, remember, number of threads to the power nk. That could be really big. So, you may need to go get some coffee, go to lunch, take a nap or something. But it turns out, when you focus your test in this way, it's pretty reasonable. So we're gonna let that guy go for a little bit, maybe come back to it. Are there any questions about what you've seen here? Yeah. Yes. Yes, chess works with unmanaged code. Yeah, so essentially the schedule is the string. It's the same. So if you remember the cap vision is the schedule intercepts, and the whole engine is basically the same for unmanaged and managed. The only difference is this wrapper. So the same string I showed you there that I used for the repro here is available in Win32. So it's the exact same experience. Okay, so again, we just need to make that work in the debugger. But currently what we have is from the command line, you can launch chess, and you can give it the exact same arguments I gave you here, breakup preemption. So you can have exactly the same experience that I'm having directly in Visual Studio by running on the command line and then just saying, please break up preemptions. So we have exactly the same vocabulary, exactly the same set of actions we can do, whether you're coming from the command line or inside Visual Studio. Yeah, at the back. The current plan of record is the CTP with 2010 team test. Yes. Question there in the corner? No? Oh, okay. In the New York hat?
For SQL Server or like IIS or large applications, have they ever taken this up? Because I saw 108 executions or whatever, execution steps, or whatever you said. What about the large applications that had millions of execution steps?
Right. So the largest we've run this on is Singularity. This is operating system, which is like, oh, question, sorry. What if you wanted to just run this on SQL Server or IIS? Where your K is 1 million or something? Again, you have to scope things properly. If you give it hundreds of threads and just, have big K and give it huge amounts of data, there's not a lot we can do. So it does have to be scoped. We generally try to have you think of scoping it in a number of ways. I have a module that I've just changed. I want to focus the preemptions there, right? So chess has the ability to scale. It can handle those codes. How many tests? What's your throughput going to be? How many tests a second are you going to get? Running an entire SQL scenario? Yeah. This goes hand in hand with sort of really factoring your code in a way that you can test at the component level. But it's a very good question. We do want to handle that scenario, but giving you the full chess experience of exhaustive search at that scale would be, I think, quite difficult. Wow, we have lots of questions and more to talk about. Just one more question, then we'll move on.
Does your algorithm scale fairly well in parallel?
Does our algorithm parallelize? Yes, it does, but we have not implemented that.
So in theory, if I had like a box computer.
Yeah. No, so we could, but again, exponentials are overwhelming, even if you have like 1,000 processors. Okay, let me do one more thing before I hand it back to Madan, and because I see that we are getting close to the end, although we have 15 minutes, so we go until 11:45. So actually, I think we're doing all right, given we've taken some questions. So please, we're gonna try and finish up here, but we want you to stick around as long as you want to ask questions. Let's do one more thing. Oh, what happened here? It did terminate, and it explored 13,000 schedules. So now we know for that test case, researchers are always about saying what the assumptions are. For that test case, we have explored all schedules with 2 preemptions, and there were 13,000 of them. And so you might be thinking, and George might be thinking if he's in the audience, did you try 3? We're going to start that running. And then we're going to go back to the talk. So I'm going to say test property, chess bound. I think it'll terminate before we're done. I tested it last night. I won't tell you what happened. We need a string there. Oh, 3, please. OK. So now I'm telling chess use 3 preemptions, same test. And let's start that running. Yeah, as the gentleman said, I see 108 execution steps. That's actually the number of synchronization operations. There's a lot more instructions that are executing there. OK, so we'll let that go. We'll switch back to the presentation. So again, story with CCR, Heisenbug existing in the system for months, if not longer. Rarely, it showed up once, and they couldn't find it again. With chess, we demonstrated, we found the bug once we had it isolated. Somebody said, I think it's in this test. We found it in a minute, exploring a couple thousand schedules. We got a repro. We could go right to the deadlock. We could go right to the preemptions, find the races, fix the bug. We showed you that we exhaustively explored all schedules with 2 preemptions. That level of coverage and sort of confidence is something really new that chess is giving us. OK, so Madan's already really said this. We've been working internally primarily with the parallel computing platform team, who are using both the Win32 chess and managed chess for testing parallel link, p-link, concurrent data structures, TPL, a number of other libraries that they're supplying. We've used it on Dryad. You heard a little bit about Dryad Link from Rick Rashid. It's been used on Singularity, which is the largest piece of code, almost 200K. And chess can systematically test the boot and shutdown program of this small operating system. Okay, and in doing so, we found some live locks. Okay. So we are announcing that chess will be available at DevLabs. We are working on the installer. We are getting it out soon. We want your feedback. If you go to DevLabs, that's msdn.microsoft.com/devlabs, you'll see a number of tools that are there. PopFly, Small Basic, PEX. PEX is also from our same team. And chess will be there very soon. Please come by our booth if you want to get more information, and we can scan your badge. We'll send you an email when the release is out there very soon. OK, so now I'm going to hand it over to Madan, who will talk about the future.
Can you hear me OK? Ah, great. So I just want to finish off with one thing about preemption bounding. It turns out that many concurrency errors you can find out with just 1 preemption. All atomicity violations, you can just find it with just 1 preemption. And the bug that Tom showed was actually a very, very, very hard bug, and we found it with 2 preemptions. So we are already in the limit of the hard concurrency bugs when you go to preemption bound 2. And so far, we have tried chess on a lot of programs. I have not been able to find a bug that required 3 preemptions but did not show up at 2 preemptions. I mean, that just goes on to show that those bugs, if they exist, I'm sure they do exist, are very, very rare. That's something not typical programmers make. And so I'll be really happy if I'm able to run chess with 2 preemptions on all the software that Microsoft is shipping. Right? I'll put it on my tombstone. Right? Cool. Right. So wonderful. So now we're going to go into the future. This is a research talk. So what you have seen so far is a tool that is very soon will be available for you guys, that you can play around with. Now I'm actually going to slide into future research land. Yeah, slightly above in the cloud. Yeah. Okay. So we can do a lot of things with CAP, and I think we're still exploring a lot of the possibilities that this power of controlling the interleaving gives us. And I told you that CAP has 2 facilities. It can record the execution. It can also direct the execution. And you'll see both of it coming in place in this tool called Featherlight. It is a lightweight data race detection tool. You guys will probably, most of you are already familiar with what a data race is. It's sometimes it's a mistake that you make when you don't have the right synchronization. So the actual definition is 2 threads concurrently accessing the same shared memory location, and one of them is a write. And there is no happens before relation. I mean, there's no synchronization order between these 2 accesses. And so here's a very simple example of a data race. I have thread 1 that is doing the example that Tom mentioned, that you're checking for the pointer p. If it's not null, you dereference it. And since you want to execute these two instructions atomically, you protect them with a critical section. So thread 1 actually enters the critical section and then does this operation and then leaves it. But that alone is not sufficient if this guy, thread 2, does not follow the same locking discipline, right? Just adding the lock in thread 1 does not solve the problem. And this is called a data race because this access by thread 2 does not follow the synchronization logic that you have for your program. And data races almost always point to underlying bugs in your synchronization logic. And so what you want is tools that can find these data races in your program. But the problem is that existing data race detection tools are very, very slow. What you need is, you not only need the cap functionality for logging all synchronization primitives, but you also need to trap every memory access, the shared memory access that a program is making. And it makes a lot of such memory access. Like 1 in every 5 instructions in your program is a memory access. So if you're doing that much processing for every memory access, it's very difficult to make data race detection very, very fast. So typical tools, they slow down by a factor of more than 10 or more. There are some tools that slow the program by more than a factor of 200 times or so. So what Featherlight, the goal of Featherlight is to be able to do data race detection when you're running your stress tests, right? And the faster you can run your stress tests, the more tests you're running. And also we want to run Featherlight with chess as well, right? Chess also has the same problem. We have the state space explosion, and if you give us more time, we want to be able to run as many interleavings as possible. So you don't want your data race detection to slow you down as much, right? So the key idea is that maybe we don't need to process all memory accesses. You only need to process those memory accesses that participate in a data race, right? It's a sort of, that's what you want to do. And so what we have in Featherlight is a neat sampling algorithm that uses heuristics to predict if a particular memory access is going to going to result in a data race. So it actually uses some predictive behavior to identify data races. And so our best sampling algorithm only processes 5% of the memory accesses, and it adds less than 30% runtime overhead. Just to compare with existing tools, like the 10 times is actually 10,000% overhead. So we just add a 30% runtime overhead, and we're able to find data races in your program. And not only that, we are building Featherlight on top of CAP, right? And CAP can direct the execution of its choice. So what Featherlight can do is that if it finds a data race, it can actually drive the program along the two possibilities. So there are two threads trying to race to a memory access. It'll say, OK, what happens if this guy wins the race or this other thread wins the race? You can try both two possibilities and see if there are the program behavior actually changes in the two of them, right? So this is very important to identify what we call benign data races. There are many data races in your program that are intentional, that the programmer is explicitly adding such data race for performance. A typical example is updating a statistics counter, right? Yes, there is a data race because of which you might lose some updates here and there, but you don't care. So these kind of errors are called benign data races, and by driving the program along the two interleavings, we can actually sort of prune away all these benign data races. And that's what the power of CAP lets you do. So that's one tool. And the second tool is called Sober. There's a saying which says that stupid programmers make stupid mistakes, and smart programmers make smart mistakes, right? And this is a tool meant for really, really smart programmers. Okay. And what it's trying to do is trying to find errors that show up because of memory models in your program. You don't want, if you're a programmer, you want to avoid exposing these memory model behaviors to your program as much as possible. But there are some people who have to put up with it. These are the guys who are writing writing the critical path in your program or writing super efficient concurrent libraries. They need to, they typically try to avoid using locks because locks are expensive. And so these lock-free programs, what can happen is that you're using these low-level primitives like volatile variables to do your synchronization. And then these programs are exposed to memory models. Essentially by memory models, what I mean is that when you run your program, your compiler can reorder instructions. And after the compiler, you run it on your processor, and the processor can reorder or delay instructions. And all these can change the behavior of your program. It's very, very difficult to find these bugs because you have to not only have to get the right interleaving, you also have to be lucky enough to to be running the program on the right processor configuration. It's very difficult to find, and not only that, they're very hard to understand because you can keep staring at the code. I can tell you there's a bug. You still will not be able to find the bug. So, so here's a quiz for you. So it is one such bug. So, so let me explain what this program is doing. It's a C# program. There are two Boolean flags, flag 1 and flag 2. They are set to false. Thread 1 is going to set flag 1 to true. And then see if flag 1 is still false. If it's still false, it'll go and do the work.
It's checking flag 2.
It's right. It's right. It's right. Okay. So, and then thread 2 is setting flag 2 to true, and then saying, okay, if flag 1 is still false, I'm going to do the work. So the question to you guys is it possible for both the threads to do the work? Oh, okay. Very smart, guys. Okay, cool. Okay. I think so. It's a smart mistake. Okay. So did everybody get that? Oh, okay. So, anyway, it's very. This program is actually wrong. If let's say if what can happen if do work is something that can only be run by one thread at a time, these two threads are using these volatile variables to synchronize, and what can happen is that this store here, this flag 1 equals true, that can be delayed by your processor. Like if you're running it on x86, it's because of a store buffer, and so this write is actually not visible to the other thread. If I give you these 3 lines, you'll say, there are some guys who say, you forgot a memory barrier, right? And so what we have done is actually we've built a tool called Sober that can find these kind of errors, and we have run it on some programs written by really, really smart people inside Microsoft. And, we found mistakes too. Okay. So if you didn't understand this, it's not your fault. Please come back to me and then come to our booth. I'll explain it more in detail. So what Sober can do is that it actually has a precise definition of what the underlying memory model is. It knows exactly what your compiler can do. It knows exactly what your hardware can do. And given a program, it sort of analyzes these interleavings as well, and then sees which of these interleavings can result in a behavior that you did not expect. So that is the end of the talk. And so at this point, I would like to take any more questions that you guys have, Tom and me. Thank you.
Sorry. For the question, let's just take a quick look.
Oh.
What happened?
Sorry. No.
It completed. It passed with 189,472 schedules, preemption bound 3.
Okay.
So George can sleep easy at night.
Okay.
Okay, questions?
Questions? Yes.
The runtime detection of deadlocks, do you also analyze the ordering, synchronization of your flag in order to detect potential deadlocks?
Repeat the question.
So the question is, we identify deadlocks that happen dynamically. So can we do some analysis based on the lock orders to actually predict, to report deadlocks that could potentially happen? We do not, but we do have an internal monitor that can actually look for lock order violations. So in the sense we have written such a monitor, but we are not making it available public. Yeah. Because there are already some other tools that can do that for you, and then we want you to use those tools. Yeah.
Second question is, instead of this reproduction, could you also generate the read down?
The question is, instead of this human unreadable string, can we actually have a dump that is more easier to analyze? Is that? Yes. So yeah. So in fact, you should actually visit our booth. We actually have something called a Concurrency Explorer that can actually visualize the interleaving for you. That you can actually take in the string and your program and actually show what the interleaving is.
But I think he's saying. But I think what you're saying is, I mean, pretty straightforward. I mean, we can take a snapshot whenever chess finds an error of the memory image. But I mean, very often the repro is useful because you want to know, sort of, as we showed, that, you know, where did the preemptions happen? Where were the races and things? So, I mean, we can do that, but then we're throwing away a lot of useful information. But certainly.
Yeah. Question.
Can that analyze what locks are not necessary? For example, if it sees that preemptions are going in an order that there is never a contention.
Okay, so the question is, can chess tell you that certain locks aren't necessary and can be eliminated?
So that is a very good question. So in general, we are looking at ways to identify performance problems or also performance opportunities. That is a problem that we are looking at, but we don't have a good solution for that yet.
A question here.
So how much of the stuff that chess can detect for you depends on running within a unit testing environment?
Okay, so the question is how much of what chess can detect for you requires running in a unit testing environment. What chess requires from you as the person testing is that you can return your system to the same initial state, which happens to be a nice property of unit tests. They always start from the same initial state. So we've run chess on much larger pieces of code. But what you need is typically what you get from a stress test. If you're stress testing a piece of code, you're running it repeatedly and you restart it. You restart your image, or you start from an initial state. So chess solves the repro problem for non-determinism in timing and threads, but it doesn't solve the state repro problem. So you need to basically provide a way in your framework, whether it's unit or whatever, that you can give us a command that we say reset. And so every time chess wants to do a new schedule, it first calls your reset.
So using it for like a GUI app or something?
Sure.
Yep.
You can do that as long as you also provide us the events you want to do.
Yep.
Right?
Yeah.
You need to control the things we don't control.
Like clicking the button?
Yeah, like
Exactly.
clicking the buttons.
So existing stress tests actually have such an infrastructure because stress tests are not interactive. So what we do is we actually use, chess was designed to, fit in with your stress testing infrastructure as much as possible. And in fact, we have seen that existing tools already, test frameworks already have this reset that Tom was talking about. And we can, if you already have such a reset, we can just call that reset. Yeah. Is a question?
Okay. Yeah, question here?
So
I've had a problem where actually running as a plugin inside of IE, pop up 97, pops up another tab, and the user does something like switches back to the tab at a particular point and causes some sort of problem.
yeah.
Is that something we could run through Selenium or something like that? Yes.
You can.
So the
Yes. Yeah.
The question is whether you could combine chess with something that was helping you do GUI testing, right?
Yes, and so it is true that we can do. If you have a framework that can control all the input non-determinism, then we can run it under control of chess. Yes. So chess relies on the, okay, so the question is, can chess work if a test requires a manual input? Chess relies on the fact that I want to run this test again and again programmatically, and so you don't want to have a manual feedback in it. Yes. So, yeah.
Question,
So question?
question here.
Okay.
For native code, chess basically, not chess, CAP, understands all synchronization primitives and controls the object protection.
Right.
Doesn't understand Windows messaging as one way of effectively passing control from a background head to foreground.
Right. So does Chess understand window messaging?
So,
Windows messaging.
so if the both threads that are using the Windows messaging are in the same process, then we do understand that. Okay. So we do understand a lot of the asynchronous I/O that goes through the kernel.
Okay.
Windows messaging is one.
Yes.
Yeah. There's lots of APIs for concurrency. We have one more minute, and then we have to stop. So we'll take one more question, and then we have a booth at the MSR at PDC in the back of the big room, and then we'll be at the experts at 6 p.m. So
Yes.
last
Please
question
do
from
come and
somebody
see
who
us.
hasn't asked a question. Yeah.
What form will the stuff that's going to be released soon take? I mean, is it integrated in the Visual Studio?
Okay.
Is it command line?
So
managed,
the question is what form is the release going to be? So we are releasing the integration with Visual Studio, but that integration relies on the command line tools. So the command line tools will be there as well for both Win32 and managed. So you'll be able to run managed code from Visual Studio, and you'll be able to run from the command line the Win32 and the managed.
x64.
x64 not in this first release. We have a whole lot of things we want to do. x64 requires some extra things. Thank you very much. We'll see you later.